All right, I'm going to try to introduce force tables and what to do when anytime you have forces at angles. Because it's very important to understand that in physics, anytime there's something at an angle, whether it be how far you go, or how fast you're going, your velocity, or how hard an object is being pushed or pulled, a force, it can be completely broken down into x and y versions or components of it. So a quick example is, let's say you're trying to get from position A to position B. You could go 5 miles northeast, but let's say it was blocked. You're still going to end up at the exact same position if you went 4 miles east and 3 miles north. It'll still get you there. In fact, we could have redrawn this triangle as 3 miles north and 4 miles east. Either way, if we look at these x and y components separately, our x component is always plus 4 miles. And I say plus because in math class you're taught that to the right is positive and to the left is negative. In physics we do the same thing. So whether you're taking the bottom path or the top path, you still have plus 4 miles because you're still going 4 miles east. Similarly, these two vertical components are going to be, you guessed it, plus 3 miles because again, up is positive, down is negative. So no matter what, we still have an x component of 4 miles east and a y component of 3 miles north, which is the exact same as this 5 miles at a northeast direction. And you can use SOHCAHTOA to figure out what that angle in there is. So you could say 5 miles at x degrees north of east. And that's what we're going to be focusing on today. I'm going to give you a little bit of a background for how to set up old problems that we used to do to introduce force tables. And then later in the video, we're going to be working with forces that are at angles and then putting them into those force tables once we've introduced them. And one more example about how horizontal forces and vertical forces are completely independent from each other is ropes or chains. And I really hope you guys start seeing this everywhere you go. Is you will never find a rope or chain hanging between two objects that's completely horizontal. And that's because horizontal forces have no effect on vertical forces. So let's say you took this right end and pulled as hard as you possibly can. The most you can get is just barely still dangling because the weight of the chain is a vertical force. So the force of gravity is always going to be a vertical force. And when it's hanging low, like it is in this picture, if you pull it at this angle, like the right pole is doing, then you do have a vertical component and a horizontal component because it's being pulled at this angle. So there is a vertical component. But as you get closer and closer and closer to being completely horizontal, notice how that force becomes less and less vertical. And eventually you get to this point where it's nearly horizontal, but you can't quite get it completely horizontal because you're always going to have a vertical force of gravity that as you get closer to horizontal, there's less of a vertical component as you're pulling it fully horizontally, which is kind of cool. So no matter how hard you pull a chain or rope, you can never get it completely horizontal. And I just think that's neat. All right. So we're going to reintroduce a familiar problem and use it to introduce how to set up a force table so that when we get to the more complex problems, you guys are ready to rock and roll. So let's look at this example. We have a 16 kilogram object being pushed along a frictionless table. Oh boy, every time I see the word frictionless, I am highlighting that. If you see frictionless, smooth, that's something to highlight. I'm also going to highlight that it's a 16 kilogram object and use my units. We have kilograms. Well, that's telling me, hey, that's the mass, and it's being pulled by an 8 Newton force. Use your units to help you. Newton means force, so we have some force there. So we have this force, and kilogram tells me mass. So we know the mass, we know the force, and now we just need to set up the problem. So I know we need to draw a free body diagram, we need to find the net force, and we need to find the acceleration. So the first thing I'm going to do is draw a free body diagram. And now that we have our forces labeled, we have normal force because it's being supported by the table. the weight of the object being held down, and this horizontal 8 Newton force, we know all of the forces. And I'm also going to make a note that the mass is 16 kilograms. So we have 16 kilogram mass. And normally you would say, oh, it's moving horizontally, which means the vertical forces are balanced, right? It's in vertical equilibrium, but not in horizontal equilibrium. So you could say, okay, we know in the x direction, those forces are going to cancel out. By the way, we should just take a minute and calculate them. If you aren't familiar with how to calculate the weight of an object, the force of gravity, well, it's mass times gravity, which is 16 times 10. By the way, for all of these problems, assume gravity is 10. So 16 times 10 is going to give us a weight of 160 newtons. Cool. And it's down, so I'm going to make sure that, hey, that's a negative vertical 160 newtons. And because it's being balanced vertically and there's no other vertical forces, well, the vertical forces need to cancel each other out. So the normal force is also 160 newtons. So vertically, the forces are balanced. The net force vertical, net force y, equals 0. And with that, that means that the acceleration y equals 0. The vertical acceleration is 0, because net force and acceleration, vertical and horizontal split, are always proportional to each other. From the equation, net force equals mass times acceleration. So if net force is 0, mass is 16, well, a little bit of algebra will show you, hey, the acceleration is also going to be 0. So now that we've gotten that out of the way, we can figure out, okay, net force x. What is net force? Net force, anytime I ask that question, people say it's mass times acceleration. No. That's how we can use it to calculate acceleration. Or if we know the acceleration, that's how we calculate net force. But net force, in its simplest terms, is the sum of all other forces. Well, our vertical forces have canceled out, and if we're just looking at the x direction, net force x equals mass times horizontal acceleration, all of our horizontal net forces is, well, this applied force from the object being pulled. So that should be 8 newtons equals the mass, which is 16 kilograms, times the acceleration. A little bit of algebra will show you the horizontal acceleration is equal to 0.5 meters per second, meaning this box is going to get 0.5 meters per second faster every second. If you didn't follow parts of what I did with this question, because I did move quickly because it's a video and you can rewind and rewatch parts, please go back and get very comfortable with this problem before we move on to the next part. And what we're going to do in the next part is we're going to take this exact same problem and I'm going to show you a cleaner way to keep all of this information organized that you can choose to use and you can choose not to use. I personally really like using them. I think it's very clean for problems that are more mixed with vertical and horizontal. So if we look at the next problem, it's how to set up a force table. And I'm telling you now, it's probably going to be tedious with simpler problems. And if you feel comfortable just skipping past a force table, you are welcome to do that, but I definitely encourage you to at least try it. It doesn't take that much time. All of your information is very clearly organized, and it helps you solve the more complicated problems. But that's on you. That's up to you to make your choice. So we're going to copy the same problem into a force table, and I'm going to show you how that force table will calculate the net force and acceleration very simply. I think I have a page. So I'm going to take 2 seconds to copy this. And now that we have the problem copied, I'm going to set up my first force table. And the way you do that is relatively simple. We're going to break every force that's acting on the object into how much of it is in the x direction and how much of it is in the y direction. So we're going to break forces down into whether it's an x or whether it's a y. And we get to more complicated problems, forces at an angle, we're going to break it down into how much of it is x and how much of it is y. How much is it being pulled horizontally and how much of it is being pulled vertically. And my recommendation is anytime you're doing this, try to save normal force until last if you can, because normal force is not always equal to the weight. It is in this problem because there's no other vertical forces, but think about it. If you have an object sitting on the ground, right now, if this is a 1 pound brick, my hand has to hold all 1 pound of it. But if I lift it a little bit with the other hand, now my hand doesn't have to support the full pound weight of the brick. So there's an applied force from my hand up that's about equal to a half a pound, 1 pound down from the weight, and my hand only has to support a half a pound of it. If you want, you can get a scale and slightly lift up on an object and see, oh yeah, the scale is reading less because a scale reads the normal force every single time. That's what a scale reads. It doesn't actually read the weight. It reads how much of the weight it has to hold, which is kind of neat. I think it's kind of neat. But I digress. Let's get into how to set this up in a force table. So number one, make sure you just draw a force table. Number two, fill in all forces along the left side. So we have the weight, we have the normal force, and we have the force of gravity. And again, I'm going to do normal force last, just so I don't accidentally fill something in that's not correct. And then at the bottom, we're going to create these sum lines for net force, because net force is the sum of all other forces. So if we know the weight, we know the normal, and we know the force of gravity, we can figure out net force. And the other thing I want to point out is that first column is all x components, and the second column is all y components of this force. So right here, we have how much of the weight is horizontal. Well, let's look at this. Force of gravity, there's 160 newtons downward, and none of it is to the left or right. So the x component is going to be 0. The y component is down, and that's going to be 160 newtons. But this is where I want to give you a piece of advice that I hope you carry through because it'll prevent so many mistakes. Are they positive or are they negative? Well, very clearly the weight is downward, and again, up is positive, down is negative, right is positive, left is negative. That should be negative 160 newtons. So before you start filling in your x and y values, I would recommend going through and filling in positive, negative, 0, positive, 0, positive, negative. Is it a 0? Is it positive or is it negative? Well, normal force is all vertical, which means this x component is going to be 0, and it's upward, so it's going to be a positive value. Oh, I mixed up. I put Fg twice. I'm so sorry. That should be applied force. Well, the applied force, we don't know what it is. Oh, we do know. It's 8 newtons. So it's to the right, so it's going to be positive 8 newtons. And because these are all forces, you don't have to fill in Newton for every single one because they should all be in newtons anyway. You can if you want, but it's a little bit of overkill, I think. And the applied force is all horizontal, which means its vertical component is 0. All right. So now we get to net force, and we still haven't filled in our normal force for the y. So the way these force tables work is you're just kind of filling in pieces as you go. And once you have an entire column filled, you can move on to say, oh, we know the net force is the sum of all forces, which means 0 plus 0 plus 8 is going to mean that the net force in the x column, or net force x, is equal to 8 newtons. We can't do that with the y yet because we don't know normal force. But another thing you should be thinking about, something I've been telling you since day one, the first thing you should think anytime you see a problem is it speeding up, slowing down, or changing direction? Now you should be thinking about in the x and y direction. Is it speeding up, slowing down, or changing direction? Are the forces balanced in the x? Well, they're not in the x. Are they in the y? Yes, it's sliding horizontally. There's no vertical acceleration, which means the vertical net force should be 0. And if this is 0, and the sum of all of these have to equal the net force, negative 160 plus question mark plus 0 equals 0. Well, this can be no other value than 160 newtons. And that's how you can use a force table to kind of figure out where your normal force should be. So now we know net force x is 8 newtons and net force y is 0 newtons. And I know, I have it written here and I have it written up at the top too. This probably feels tedious for simpler problems like that. I get it, but it will help you with more complex problems. Now, there is one other tool that we can use with our force table. All you have to do is add one more row for acceleration. And remember, from the net force equation, net force is mass times acceleration. If we just take our x net force and our y net force and divide them by the mass, that will calculate the horizontal acceleration and the vertical acceleration. So 8 over our mass, which was 16 kilograms, will give you an acceleration x of 0.5 meters per second. And we can do the same thing in the y direction. 0 divided by 16 is going to give you 0. I went through this relatively quickly, but I think I took my time with it. But again, I encourage you that if you missed parts of what I was doing or you didn't know why I was doing them, now that you've seen it through to the end, go back, rewind it, watch it again. Because next we're going to make this a little more complicated, and we're going to apply it to forces at an angle. Before I move forward, I cannot reiterate this enough. If you are not familiar enough with SOHCAHTOA and how to use it to find the x and the y when you're given the hypotenuse, you need to go watch a couple videos, get comfortable on that, then come back to this. I'll try to put a comment down below of 2 videos I really like for SOHCAHTOA. They should be in my course pages, but I'll add links to those videos in case you do want extra practice with that. Go watch those, then come back to this. But if you are comfortable with SOHCAHTOA, we're going to move forward. So now we're going to take that exact same problem and we're going to redo it if instead of the force being 8 newtons completely horizontally, it was at 30 degrees above the horizontal. So you're still pulling with 8 newtons, but 30 degrees above the horizontal. And we're going to find the net forces. When I say forces, I mean what's the net force x and net force y. And we're going to find the acceleration. And depending on how that's going, we might have a horizontal acceleration and a vertical acceleration. So let's actually do that. Let's copy that problem over to this. Give me 1 second to copy it. All right, so now that we have all of these, now that I've redrawn it, let's go through and follow our same steps. Number 1, always need a free body diagram. Number 2, you can set up your force table. And when I'm doing my free body diagram, I am being thoughtful of, okay, what can I figure out while I'm drawing this? Clearly I can figure out the weight, and I know that the applied force is at an angle, and anytime I see something at an angle, I'm breaking it down into the x and y components, and we know that that's a 30-degree angle in there. So let's start filling in our forces. I would say that's your third step. Fg, Fn, and Fa. And now I'm going to fill in my positives, negatives, and zeros. Positives, negatives, zeros. So weight. The vertical is going to be negative. The horizontal is going to be 0. Normal force. The vertical is going to be positive. The horizontal is going to be 0 because it's all up and down. None of it's left and right. Again, x and y should be held completely separately. And the applied force, that's at an angle, but it's up and to the right, which means some of it's to the right and some of it's up, which means it's going to have a positive x and a positive y. We don't know what those values are, but with SOHCAHTOA, we can use this 30-degree theta, and we can use this 8 Newton hypotenuse to figure out that the x component and y components should be 6.93 newtons and 4 newtons respectively. I encourage you to try that on your own calculator, because if you're not getting those values, make sure that your calculator is not in radians. Your calculator should be in degrees if our angle is in degrees. Obviously, if your angle is in degrees, which that would be pi over 6, then you would be using radians. We'll get more into radians versus degrees later, but for now, make sure that you're getting it right. And then I'm going to keep going. And we know, okay, well, the weight is 160 newtons. So 160 newtons downward, and we're just going to keep trying to fill in pieces as we go. Net force at the bottom, acceleration is in the row after that. So now we have this unknown normal force. We know that there's 160 newtons of weight down and 4 newtons upward. So we know that it's definitely not getting lifted off the table by the vertical component of the applied force. I probably should have brought those numbers a little bit closer together, but this is fine. So it's not getting lifted off the table, which means the table does have to support it. So this isn't going to be 0. It's not going to fly off the table, which means that it's not going to accelerate vertically, which means the net force vertical, net force y, is going to be 0. So if we know net force y is 0, we only have one unknown value in this vertical category. So negative 160 plus question mark plus 4 equals 0, because net force is the sum of all forces along that axis. So this has to be, by a little bit of math, 156 newtons upwards. Now let's break it down into the x direction. We have 0 plus 6.93. Well, net force is the sum of all forces, which means net force x is 6.93 newtons. And using net force equals ma for the x components, we can figure out that 6.93 divided by 15 gives us an acceleration of 0.46 meters per second. Earth's going to get 4.6 meters per second horizontally faster every second. Good. So always be extremely cautious about the normal force, and I hope that helps finding x and y components and how to keep them more organized, because even looking at this page, it should look more organized than this mess that we had going up here. Okay, so now the next thing I want to introduce, by the way, this should be all you really need at this point, but I'm going to kind of jump into the next thing. So that way I can put all of this stuff in one video. It's clean, it's neat, and it's all together. What if we have x forces, and what if we have a net force that's not all in the x direction, but you have some net force horizontally and some net force vertically, because that's going to happen. And the way you do that is to undo SOHCAHTOA, or more often use Pythagorean theorem. So let's look at this example problem. From a top-down view, we have two people trying to pull a non-stubborn donkey, which means he's not resisting. He's just going to go with whatever they pull along a smooth surface. And I'm going to highlight smooth surface because I know that's saying, hey, friction equals 0. One person pulls it to the right with 10 newtons of force, and one pulls it straight up with a 5 newton force. And by the way, this is an 8 kilogram donkey. I forgot to include that, but that's what we're working with. What is the direction of the acceleration, and what is the magnitude of the acceleration? Or what is the magnitude of the net force? So let's draw this out first. So we're going to have our donkey here, and one person pulls it to the right, and this is a top-down view, so let's make sure it's a top-down view. One's pulling it to the right with 10 newtons of force, and one's pulling it up with 5 newtons of force. And if we put this into our x and y table, we're going to call this the force of person 1, F1. We're going to call this the person 2, so that's F2. F1, filling in our positives, negatives, and zeros. F1 has 0 y component and plus 10 in the x direction. Person 2 has 0 in the x, but plus 5 in the y direction. And right now we can jump straight into net force, combining our x's and y's. So 0 plus 10 is 10, 0 plus 5 is 5, and here we finally have a situation where we have net force x and net force y. Well, how do we do that? Well, if we go back and redraw our original diagram of the donkey, there's a donkey's head, there's his big ears, and there's his 4 legs, because this is a top-down view. This is going to be our net force drawing. This is separate from your free body diagram, because net force never gets drawn on the original diagram. But our net forces, we have 10 newtons to the right and 5 newtons up. Just like if you were going in that original drawing 10 miles east and 5 miles north, it behaves the same way. Well, we can use reverse SOHCAHTOA and Pythagorean's theorem to figure out how many newtons is it being pulled at this angle. And using Pythagorean's theorem, which in case you're unfamiliar with it, a squared plus b squared equals c squared, and mathing that out, we should a net force of 11.2 newtons. So now our net force total is 11.2 newtons. By the way, this is what the term magnitude means, the total amount, the number. So we have 11.2 newtons is the magnitude of the net force. But what is the angle? Well, you can see he's being pulled east, but he's being pulled north of east. So it's going to be at some angle theta north of east. And we'll go over the naming convention in another video, but I wanted to introduce it now. And using SOHCAHTOA, we have the opposite and we have the adjacent. So I'm going to use tangent. So tan theta equals opposite over adjacent. Tan theta equals 5 over 10, or 0.5. Now, to undo a tangent, you need to do an inverse tan. So tan negative 1 of tan theta on the left, and on the right, whatever you do to one side, you have to do the other. So we're going to do the inverse tan of the right side too. The inverse tan of tan cancels out, and we're left with theta equals the inverse tan of 0.5. And if we plug that into a calculator, again, making sure you're in degrees, you should get an angle of about 27 degrees. I know that I went through that quickly, but again, I want you guys to be familiar with SOHCAHTOA, and if you're not, you should figure out how to be, you should go back and watch some videos on getting familiar with SOHCAHTOA and then come back to this. So we're just using inverse SOHCAHTOA or reverse SOHCAHTOA to find that that angle is 27 degrees north of east. So the resultant force, the total force, is 11.2 newtons from Pythagorean's theorem at 27 degrees north of east. Okay, I covered a lot of material in this video, but please feel free to go back and rewatch parts of it that you need. I hope this helps, and if you want clarification on any part, reach out to me, let me know, and I will try to clarify the finer details and hopefully make this make a little bit more sense. And other than that, I hope you enjoyed it. Have a great day. Bye.